Good morning, everyone. Thank you so much for coming to my thesis defense. So, during my PhD research, we focused on developing a framework, a generalized framework for cerebral aneurysm geometries, and which supports CFD simulations. So, in my presentation today, I am planning to introduce you to the key concepts of our work, as well as some results along with the conclusions we were able to get. And I will be dividing my presentation into three main sections. The first is I'm going to introduce the anatomy and the geometry essential for my work, and then I will move into an independent section that discuss about the mathematical framework that I will be using. And finally, we have this third section that is an important part, as I will be presenting the two-dimensional geometry that we have proposed. Right, so what is actually an aneurysm? It is a structure in the body that happens when, it is kind of a balloon-like structure in a blood vessel. So, usually when you have a blood vessel, sometimes certain place in the blood vessel will start to pump and blood will fill in and eventually lead to a structure like this. It's basically kind of a berry hanging from a tree. So these aneurysms can happen in many parts, many areas of the body, such as blood vessels in the brain, in the heart, intestines, kidneys, and so on. Now, for my research work, we are only focusing on cerebral aneurysms, that is, the aneurysms on the brain. Now, the big concern about aneurysm is this second bullet point. If it is life-threatening, if it gets ruptured. So, like, let's say if a patient got diagnosed with an aneurysm, then the next big decision they have to make is whether to undergo treatments or not. Now, someone might say, just like an appendix, why don't you directly operate on an aneurysm as soon as you heard the news, right? But the thing is, we are talking about cerebral aneurysm, that's the brain. So we do not want to do anything unless it is extremely necessary. So that is why a proper tool to analyze the hemodynamics around this region is important. And now here are some statistics related to cerebral aneurysms. You can see that the annual rate of rupture is around 8 to 10 people per 100,000. And about 15% of the people will die with, 15% of the people with a ruptured aneurysm will die even before reaching the hospital. So that's a serious case. Also, an estimated number of around 6.5 million people in the US alone have an unruptured aneurysm. So it's about 1 in 50 people. So that's quite a large number. So if we are going to do treatments for all these 6.5 million people, that's going to be a big problem. So as I mentioned earlier, a proper way to analyze the blood flow is necessary. Now, let's take a look at this anatomy related to the cerebral aneurysms. The image on the left hand side is the inferior rib of the brain. That's the image taken from below. And here anterior means the front, posterior means back. So this is the front side of the brain. And this part in the middle is called the circle of Pitts. And it's a loop. So as far as I know, there is no other part in the human body that has got a loop in it. So this is kind of a very special biological structure in the body. And the image on the right hand side is the kind of zoomed in image of the circle of Willis and the associated focus on this kind of a region that has got a like a junction in it. So we call this as a bifurcation, and you can see similar structures appearing in different places in the circle of Willis. And if we focus on this part on the top corner, we call this artery as anterior communicating artery, or in short ACOM, and you call this as A1 and A2. So basically it's A1, A2 and A3 in this bifurcation. So from here onwards, if there is a bifurcation, I will call the main artery as A1, and then, so this is a scanned image of an actual aneurysm. So here you have the bifurcation. So I'm going to call this main artery as A1. The one on the right hand side is A2, and the one on the left hand side will be ACOM. And also in this structure, blood flows from A1 towards this branch, and it divides across the two branches, A2 and ACOM. Now, if we need to feed this structure into a computer system, we need to have a proper way to identify the key features of this aneurysm that are called parameters. And we can...
Hey, thanks. I've got a question. So you're showing the aneurysm in this example as occurring at a split. Is that more likely to happen? Is the aneurysm more likely to happen at a split than just somewhere else?
Well, now there are things called side wall aneurysms as well. So it's simply you have a blood vessel and you have that balloon-like structure. But when there is a junction, like a T junction, we can imagine like blood going from this side, and it always pushes the wall in front. So it's somewhat more likely to see an aneurysm in a bifurcation, but I don't have the exact statistics about the bifurcation aneurysm and side wall aneurysm, but you do have side wall aneurysms as well. Right, so now when identifying the parameters related to this aneurysm structure, we have several important values like the diameters of the vessel and length of the neck of the aneurysm. We have the height and the width, that's the maximum distance between the two side walls. And also there are some values that are not that obvious. Like for example, if you take the length of this structure, we actually don't. If you take a blood vessel, it doesn't really have an end to it. But for the computational purposes, we need to specify a certain quantity. And from the literature, we saw that it is reasonable to take it as a multiple of the diameter. And that's what we have done. Then we have the measurements of curvature, and on this side as well as at the neck. And a similar measurement can be extracted out from the left-hand side as well. And also for these radius values, once again, we can take it as a multiple of the diameter. And anyway, I'm going to talk more about these parameters and how we construct the model later on in my presentation. Right, so now as we have a way to identify the quantities related to the aneurysm, next is how we are going to model this aneurysm structure. There are basically two types of modeling techniques that people have used. One is patient specific and the other one is idealized. So Those are the two main types of geometries that we have and models. So when it comes to patient specific, what they do is they feed a sequence of scanned images into a sort of a design software and it extract out the boundary to create an accurate 3D object. And here I want to emphasize the fact that when creating this patient-specific model, they usually don't input the values like the diameter or the neck length of the aneurysm. They do not do that. But once this model is created, they can measure those values if they want to. Now, once we have a patient-specific model, and if they want to calculate something like pressure values along the wall, they can do that. It is possible. But the problem is, it is not possible to answer a question like what happens to the pressure when we increase or decrease the neck length. So, that sort of a flexibility is not there when it comes to a patient-specific model, because it's more or less similar to pouring liquid cement into a mold. So you have a very nice, good structure, but you cannot generalize it. So this problem leads us to an idealized geometry. So this is something we created. So all the boundaries and everything are represented by functions. So that gives us more flexibility. For example, now this is a picture that I have extracted from a real paper. And what they have done is, in the process of creating this model, they have used cylinders as blood vessels and a sphere as the aneurysm, and they have combined them together to construct this model, which is a very common thing that people do. So although this gives the flexibility, the problem is it doesn't look realistic or applicable. So what we did was, we took the good qualities from both. We managed to construct a two-dimensional model that looks like the real ones, and at the same time it gives us more flexibility to change the parameters. So before moving into creation of that geometry, I would like to take a break from the aneurysms and discuss a bit about some interesting mathematical concepts we have used in my research work. And actually the things that I am going to discuss now are kind of independent of the domain we choose. We can have a bifurcation, we can have a bifurcation without an aneurysm or with an aneurysm, or we can even have a cylinder or a rectangle, it doesn't really matter. Okay, so as we are modeling the blood flow in the vessel, which is a fluid, there should be a governing equation to represent this environment. And in this case, it's the famous Navier-Stokes equation. And what you can see on this slide is the dimensionless Navier-Stokes equation. Dimensionless because it helps with running a lot of simulations efficiently. Now, here are the main assumptions that we need in formulating this Navier-Stokes equation. So we have to assume the continuum hypothesis, and then fluid should be incompressible and Newtonian. Then we have the important parameters. The most important one is the Reynolds number, written as a ratio of the scaling constants, density and the viscosity. So we have this equation to represent our fluid flow. Now, how do we solve this equation? Now, finding an analytical solution to this equation is actually an open problem up to this day. It is in fact a Millennium Prize problem. So basically, if you can find a smooth, globally defined solution for the Navier-Stokes equation, you are going to get $1 million. So, but anyway, we have very well defined, accurate numerical solutions or numerical approximations that we can use to solve this equation. And in my case, I have used a special Python module called DolphinX that is created by the Phoenix project. And it is a Python-based environment for finite element analysis. There, the DolphinX module uses a special technique called incremental pressure correction scheme to efficiently solve the Navier-Stokes equation. And in that process of solving the equation, these are the key features that we cover. We have to generate a mesh, and then you have to apply the boundary conditions, and you have to formulate the problem, and step forward in time to solve the nonlinear system. So you mainly convert it to a system of equations and so on. So for the mesh generation, this is the domain that we create. I will explain
I have a
later.
question.
Yes.
Sorry, before we move on, what is the boundary condition you use? Because depending on how the surface
Yes.
of the,
Yeah,
what
I
that's-
will. Thank you
Oh,
for the
you-
question. I am going to tell.
Oh, I'm sorry.
It's okay.
Yeah.
Thank you for the question. Right. So now, when it comes to the generation of the mesh, this is the domain that we are going to create. I will explain it in the third section of the presentation. So once we have this sort of a domain, we can use a computational mesh on that domain. And for my work, we have used an open source finite element mesh generator called GMSH. So that's how we have obtained this mesh. Then we have to apply the boundary conditions, as well as we have to identify, once we have the mesh, we first have to identify the inlets and the outlets on that mesh along with the wall, and then we have to apply the boundary condition on this mesh. So in our domain, when you have a bifurcation, the place where blood starts to come in through the A1 is the inlet, and these two, that's A2 and A-com, the end of those two blood vessels will be the outlets, and everything else around here will be the boundary, will be the wall. Then we have to apply the boundary conditions. What are the conditions we have in these boundaries? Now, the way this code works is, we have to specify the pressure values at the inlets as well as the outlets, and then the no-slip conditions on the wall. That's how this DolphinX module perform the calculation to solve the Navier-Stokes equation. Did I answer your question?
Yeah.
Okay, good. Right,
Why do you choose a no-slip condition? Is that how blood actually works?
Yes, because now when the blood flows inside the, let's say, a tube or any fluid, it kind of creates a tiny layer close to the wall that doesn't actually move.
But that's actually what happens, that's not a mathematical simplification.
I think that's what actually happens, as far as I know. Right. Now, so once we have these boundary conditions defined on the mesh, next step is to use the step forwarding criteria. Step forwarding means you start with the value at a certain time step, and you perform some sort of a calculation to find the value of u and v in the next time step. That's basically step forwarding in time. And this is the place where DolphinX use that special incremental pressure correction scheme. And what they do is, they start with the given initial condition, and they find a temporary velocity ignoring the divergence criteria, Then using that temporary velocity, they calculate another pressure value. Then using that pressure value, they evaluate the correct velocity and the pressure at the next time step, which is divergence free. Because in the Navier-Stokes equation, we have specified the divergence free condition. So that's a pretty standard technique. And what I have newly added is the stopping criteria. Now, when this process continues, we want the solution to be stable. And stability is considered when the time derivative of the velocity as well as the pressure does not change when you progress with time. So to achieve that stability, one thing you can do is you can just put a very large end time and let this calculation do its like this, all these for loops until it reaches the end time. That is possible because eventually the solution will anyway reach the stability. So that is computationally expensive because each of these iterations take a lot of time to do, to calculate. So if we just let it run until a very large end time, and if the solution reaches the stability before reaching the end time, it will still calculate until capital T. So that's a waste of computational power. So what we did was, at each time step, we check whether the stability, or in other words, at each time step we check whether the time derivative of the velocity and the time derivative of the pressure is small enough. And if it is small enough, we break the loop and we do not let it continue to run up to the end time. So that way it will avoid the unnecessary calculation while achieving the stability. And finally, at the end of this calculation, we are going to have pressure values and velocity values across all the points or across all the nodes in the mesh. Now, with those values, next we are going to calculate another measurement, especially using the velocity values that we have calculated. Right, so the important measurement we are going to calculate is the flow rate. Flow rate is basically the rate of transfer of material from one side to the other, and it is always normal to the plane that we are going to consider. So it can be calculated as the integral with the velocity dotted with the norm, right? And as we have already found the value of the velocity, we can perform this calculation. And now this is an important part, an important point. So when it comes to our domain, we have an inflow from the A1 and we have two outflows. So since the mass is conserved, we have this relationship. So whatever comes in should go out. So basically, if we know two values, that's enough. We can evaluate the other value, right? So later on, I will be talking more about flow rates. So I will only mention about two flow rates because the third one can be calculated directly. Right. Now the last bullet point. Now here we have a small problem. Now later you will see I am going to introduce and create 2D geometries. And we have to talk about the flow rates in 2D geometries. But the problem is the flow rate defined like this is a three-dimensional quantity. So the dimensions are in 3D. So like milliliters per second, it's a three-dimensional quantity. So we had to come up with a way to convert the flow rate, 3D flow rate into a two-dimensional flow rate. So, but we did was, to answer that question, we use the Hagen-Poiseuille equation. Now, this is simply the Navier-Stokes equation along a long cylindrical pipe or a rectangle in the case of 2D. And for this particular specific case, you have an analytical solution. So it's very well defined. You have an analytical solution. So you don't have to think about numerical calculations there. And since we have an analytical solution for the value of u, we can calculate the pressure and the flow rates using that analytical solution. And this is the result they have with respect to the Hagen-Poiseuille flow. So, when it comes to the 3D cylinder, this is going to be the pressure difference across the 3D cylinder. And when it comes to the 2D rectangle, this is going to be the pressure difference across the 2D rectangle. Now, to get a relationship between the 3D and the 2D flow rates, what we did was, we equated the two pressure differences across the 3D and the 2D object. Why? Now, the reason is, when it comes to the bifurcation geometries that we are going to consider, we always, now if you want to convert between 3D bifurcation and the 2D bifurcation, we always specify the same pressure conditions across the vessels in the 3D case as well as the 2D case. So we are going to have a same pressure difference in our domains as well. Therefore, we use the same criteria because as we are comparing, as we are equating the pressure value, pressure differences across the 3D object and the 2D object, we equated the pressure and we got a relationship between 2D flow rate and the 3D flow rate. And I will show some comparisons later, and they gave some very accurate values in the bifurcation domain. Yes.
So, if instead you had thought of the flow rate, the flow in the 3D cylinder as just radially symmetric, so it's a function of just two variables, the radius and theta. So in that case, would you get the same type of equation by converting the 3D Navier-Stokes equation into the two variables? Or not?
Top of my head. I'm not sure about that process.
Okay, just.
Yeah. Okay.
I don't think you can make that simplification though, because you've got the juncture.
Yeah, but
So you
he's
lose
not
the-
working at the junction.
Yes.
To do
Yes.
something.
Hagen-Poiseuille is actually 1D. It's 1D in the radial direction for the velocity field, and 1D in the axial direction for pressure. So it actually, when you solve for Hagen-Poiseuille, you will throw away the other two dimensions in 3D. And likewise, you throw away the second dimension in 2D. It's a simplifying assumption to get a solution to Navier-Stokes for this simple geometry. So if you wanted to include the other two, there exist other solutions other than Hagen-Poiseuille for the cylinder. All of those would be, for a certain range of Reynolds number, would be stable, or sorry, be unstable, and this is the only stable solution.
So what you're saying is it's actually a transformation of the equation.
It's a very creative assumption to find a solution that turns out to actually work. It's, yeah.
But there's an R in that bottom equation.
Yeah, he defined R as the half height of the 2D.
Yes.
Right, but you said that it's really, Hagen-Poiseuille is a 1D thing.
Yeah, the pressure drop varies only in the axial direction. The fluid velocity varies in the perpendicular direction. In 2D, it would be the vertical direction. But when you compute the actual pressure drop, it turns out to just be that constant. It does depend on how high it is and how long it is. But it's all, if you took any vertical slice, you have the same velocity profile. If you took any horizontal slice, you have the same pressure profile.
But the velocity profile should change with
In the vertical
distance from
Right,
the
because
right.
of the slip condition.
Yeah, it is.
Yeah, it's still parabolic. But
Okay. So now, as I moving forward, the 2D geometry, we can safely use this 2D flow rate because we have convection. And then now I'm going to explain how to use these flow rate values as boundary conditions. Now, in the model that I explained earlier, I mentioned that we have to specify pressure values on these inlets and outlets. But the problem is the pressure values across bifurcation is not something we can easily find. I mean, in the literature, they don't usually have that information, the pressure across bifurcation. But what they have is a lot of details about the flow rates. So we had to come up with a way to convert the data that we have into something that we want. And for that, this is what we did. We first define a function that takes in pressure values, P in and P2. So the input for this function is the pressure values. And it solves the Navier-Stokes equation using those pressure values as boundary conditions. Then once it solves the Navier-Stokes equation, you have the U, therefore you can calculate the flow rate. So we have the flow rate as an output from this function. Next, we define a second function for a given flow rate value. For a given flow rate value, let's say Q, we define a second function FQ, yeah, that also takes in pressure, this pressure vector in the sense it has two components in it. And it operates like this. So since the value of Q is given, you have that same given Q minus F1P. So F1 is the function that we defined earlier. And that means the output of F1 is also a flow rate. So basically this is a difference of the two flow rates. So if we minimize FQ, and in our case we use the Nelder Mead method, multivariable minimizer, the minimum of this function will be 0. Technically it should be 0. So 0 means, let's say that minimum is achieved at P0. So at P0, this equation holds true. In other words, for the given flow rate, we define the function and we were able to figure out a value, a new value for P, so that it gives this flow rate value we started with. So in a way, we were able to figure out a suitable pressure value for these boundary conditions, so that when you use those pressure values and solve, the answer will give the flow rate value you want to have. So that's how we use the data in the literature, that is flow rate values, to something that we can use in the numerical solver, that's the pressure rate. Okay, so now we have another problem here. So now these are the two main criteria to solve this problem. If you already have the pressure values, you can directly use them as boundary conditions, solve the Navier-Stokes equation and obtain the solution. And if you don't have the pressure values, if you only have the flow rate values, you can first convert it into the pressure values by using the algorithm I mentioned earlier. Then it's the same criteria. But the problem is, this takes time. Like this takes around 10-15 minutes. This is going to take about 2 hours because there is a minimization that will be carried out in here. So now the thing is, if we have lot of simulations to run, that's good. This, and if we are only dealing with this second criteria, it's going to be less efficient. So we used a nice technique to get away with that. Now what we did was, suppose we have a set of flow rate values to work with. Then what we did was, we first choose the minimum and the maximum Q in values. Remember, we are only dealing with Q in and Q2. And then we choose the minimum and the maximum Q2 values. And at these specific 4 points, at these specific 4 flow rate values, we calculate the corresponding pressures using the algorithm I mentioned. So it's only 4 calculations. But we have a lot of flow rate values we have to deal with. Then we discretize this plane. So this is the pressure plane and this is the flow rate plane. So we discretize this pressure plane and we got values in this pressure plane. And once we have pressure values, you can directly use this first technique to directly solve the Navier-Stokes equation and back calculate the flow rate. So going from here to here is less time consuming than the first one. This process we did only for 4 values, and for everything else we got help from the discretization in the pressure plane. And now here is an actual example that we did. We had, these are the 4 flow rate values that we chose, and with respect to those 4 flow rate values, these will be the pressure values that we got. And then we discretize the pressure plane and we back calculate the flow rate values. Now the thing is, we cannot guarantee that everything is going to stick inside this domain. I mean this quadrilateral, that's not possible because these relationships are not linear. However, now we have lot of flow rates values and corresponding solutions obtained through this mapping. And we only did 4 time consuming calculations to get everything settled down in here.
What's the physical meaning of a negative pressure here?
Oh, okay. Right, that's a good question. Right. So now kind of talks about the non-dimensionalization as well. Now the thing is, we always specify the pressure mainly as a pressure difference. Therefore, what we do is we force this T-com to be 0. That means, so if I say this is 1 and this is -2 and this is 0, that minus represent it is less than what they have in the P-com. Right. And then, so now we have a self-contained criteria to solve the Navier-Stokes equation, and if we either have flow rates or pressure values, we have a method to calculate the answer to the Navier-Stokes equation. Now, once we have that answer, we can do further post-processing. So, here an important measurement that we can calculate after solving the Navier-Stokes equation is the shear stress. So, shear stress is basically the tangential force applied on the ball. And this is how it is calculated. Here we have the quantity called sigma, that is known as the stress tensor. And stress tensor actually describes the internal forces within the fluid and including the viscosity and everything. So as we already know the value of u, you can calculate the stress tensor. Therefore, you can dot it with the normal to calculate the traction, and then you can once again dot it with the normal to compute the normal stress, that's basically the pressure. Then you can subtract this normal vector from the traction to get the shear stress. So, like, why do we worry about this shear stress? Now, imagine a balloon filled with air. So, if we keep filling the balloon with air, it will burst, it can burst due to the air pressure inside. That's the normal. But now suppose you have a balloon filled with air, and if suppose I took an eraser and rubbed on the surface like this, and that can cause tearing of the walls, and that can also lead to rupture. So that's why we worry about the shear forces as well, not only on the normal forces.
Yeah, but your model does not deal with the junction, right? It's only dealing with the three tubes that lead up to the junction, right?
Oh no, I am modeling the aneurysm as well. So that means I will be calculating the flow rate values, I will be calculating the velocity values of the blood inside that aneurysm model. So the blood will cause a shear stress on the wall, and if I want to analyze something related to this rupture, this measurement is going to be useful. Did I answer your question?
Well, the simplifying assumptions you made in taking that 2D model, is that valid outside of the three tubes as well? Is it valid near the aneurysm?
It was. Yes, we compared with the 3D values and the 2D values, and it gave similar answers. Similar solutions. I have the result in the presentation.
You mean both the numerical simulations and 3D and 2D gave you the same?
Yeah. That's a good question. So now we have all the tools to move into the 2D geometry. So now, why do I need a 2D geometry in the first place? One reason is solving the 3D is computationally expensive, and the other important thing is it is extremely difficult to create a realistically looking 3D geometry with the flexibility to change parameters. Now the question is whether it is accurate. So if we are going to handle everything in the 2D sense, does it capture the essence of the 3D model? And that's the question I'm going to answer next. Now, for that, what we did was we created a 3D geometry, what you have on the right hand side. Like here in this equation, we just attach 3 cylinders to get the bifurcation structure. And then across this bifurcation plane, we got the measurements that are necessary to create this corresponding 2D structure, and here this one we created just by connecting 3 rectangles. Later on I will be improving this domain. And then we apply the same initial conditions to both and calculated the shear stress and the pressure values along the walls by solving the Navier equation. Then we repeated this process for various, by varying the angles in the 3D geometry, hence by obtaining different patterns for the 2D geometry. So all the graphs gave a very like a close relationship between the 3D structure and the 2D structure. So here the red colored line represents the 3D model, green color one is the 2D model. So you can see that they really, like, it works really well. So this approximation works really well in this setting. And also this will work as a justification for the flow rate conversion as well, because we are using those initial boundary conditions to construct this calculation. So, and we notice that this same pattern follows across all the variations that we obtain for this 3D domain. But we have a tiny problem here. Now you can see in these places there are jumps in the shear stress. So these places correspond to the sharp corners of these models. And in reality, we don't anyway have sharp corners in the surfaces. So this leads us to our next topic, which is constructing a smooth geometry. That means I'm going to create a smooth domain of the bifurcation as well as the aneurysm, and then I'm going to attach it to the sharp corner. I will explain all these things, what they mean by these values soon. Now, if we focus on creating the bifurcation domain, what we can do is we can simply start from the given specified point, and we know the L, so go up, and from here construct a perpendicular, because we know the R value as well, and then you can get the center of this right hand side circle, and since this value is given, you can move this radius line with an angle phi minus theta, and then you can move along that direction to get the point C. So basically you have B and C and the angle between them, hence you can construct all these points by discretizing the angle in between. I think in our models we usually use 40 to 50 values to approximate these curves. Then similarly, we can follow the same structure. Start from here, draw perpendicular to the radius with the length L1, get the D. Again, a perpendicular D1, because these values are known. So likewise, we can continue the procedure to obtain this smooth domain. And here are some examples of the variations of the domains we were able to get. Like you can clearly see, now here we have a very good flexibility in this domain.
I have a question. What's the reason for using circles? Circles you said smooth, but they are actually not smooth. But the curvature changes. People would use cubic splines for this kind of thing to make it smoother. No,
Well, if you look at the images,
it doesn't matter.
if you use a cubic spline, you just get basically a circular sector. He showed an image earlier where you see the bend, and you put a circle in there and it fits quite well.
Yes. Yeah. Thank you for the question.
I think smooth means one derivative.
Yeah,
Is that the concern?
Yeah, well, okay. I mean, usually people try to fit more derivatives,
Right.
and like this is dangerous for the intersections because you would have to suddenly change the width. So we actually have to design roads using cubic splines, not circular ones.
Okay. So the next task is to construct the aneurysm. Now, these are some of the variables that I introduced earlier, and there's one more thing that I didn't mention earlier. That's this direction of flow. So that's mainly the direction. So here, as the direction of flow, we take it as the tangent direction to the A1 vessel. That's considered as the direction of flow. Why do we need the direction of flow? Because with respect to this vector, we define a quantity called aneurysm angle. That's how much the height is going to deviate with respect to the flow direction. That's why we need this extra quantity. And right, so once we have these details related to the aneurysm, this is how it looks like when you construct the mathematical model. And please note that here I have labeled my aneurysm A, B, C, D, and E. And these extra purple lines I'm going to explain next. Right, so how do we start constructing this aneurysm? So we construct this aneurysm independently to the bifurcation. We create this separately, we have the bifurcation separately, and then at the end we attach them together. That's what we are going to do. We start with A and E, and we know the length between them, so we can position them accordingly. Then, similar to the bifurcation curvatures, this smooth neck transition can be done similar to the method that we did in the bifurcation. You have A, you have R, get the normal, and you have the center, then, and also you have the angle, so you can find the value of B, and since you have the angle in between them, you can construct all these points. Similarly, you have the neck on the left hand side as well. Next, as you know the positions of the values A and E, that's the start and the end point of the aneurysm, we get the midpoint. It's actually not a must to get the midpoint, you can get any ratio you want, but for our purposes, we took the midpoint. And from the midpoint, draw the flow vector, and with respect to the flow vector, deviate an angle theta A, that's the aneurysm angle, and along that direction, move H length, H units to get the C. So now we actually have A, B, C, D, and E. So we actually have all these points. What remains is the two side walls. Now to construct those two side walls, we use another way I described earlier. Then in that aneurysm, this function output the width. So that totally depends on the values of the control point. Then if you want to have the control points so that it gives the width we want, what we can do is, we can once again come up with the minimization function so that the minimum of this function gives the correct width that we want. It's almost the same thing as we did in the flow rate case. So now we have the entire structure. We can construct this aneurysm shape for a given width and with a given height. So these are some examples of different types of widths, and everything else is constant. I have changed the width, and you can see that there's a clear difference between the pictures. And so the next final task is to connect the aneurysm into the bifurcation. Here what we do is, we parameterize the top wall. This is the top wall, and with respect to that parameterization, define a point where you want to start, and from that starting point you go forward and backward, so that the distance between these two will be the aneurysm neck length. Aneurysm neck length is a straight line, not taken along the curve. Now we have the start point and end point. Then you can construct the aneurysm on this top wall according to the way I described earlier. So now these are different combinations of the starting point. Here it has moved to the left, this is the center, and here the position has moved to the right. Now, so here are some comparisons with the actual images. That's why I said this is very kind of accurate. So here this is an actual image, and by using the parameters, we constructed the domain. And if you superimpose each other, you can see that especially the aneurysm kind of is a very close match with the actual domain. And here are some more examples. This is located a bit away from the bifurcation, but still we can have the aneurysm shape replicated in our domain. Once again, we have a wide neck aneurysm. It's a good match. And then this is a patient specific model that they have created. But still, we can extract out all the details of all the parameters of this aneurysm, and you can see it still resembles the aneurysm shape very well. And finally, this is a silicon model that they have created, but still you can get the shape. So the model that we have proposed kind of accurately describes the 3D geometry that we actually have in reality. And now here are some different variations of net. Now the purpose of this slide is to show that how this model can be used for further analysis. So for example, I remember I mentioned at the very early set of slides, we need to have the flexibility to change the quantities in the domain and evaluate values on it. So here, this is an example to showcase that. So here, we chose the wide neck aneurysm, and I kept everything as the same except for the neck length. And you can clearly see that these these are streamlines plotted on a zero color plot that represent the velocity values. So you can clearly see there is a difference. So like this, you will be able to change the parameters in a realistically looking model and see how those measurements are going to vary. Also, we can even calculate things like shear stress and the pressure values, and then get an accurate figure or accurate representation of our three-dimensional case. So now I believe I have established a good framework that can be practically used to run a lot of simulations and obtain clinically helpful data. And so in the future, this model can be improved into a pulsatile flow because that's not something that we have incorporated. And maybe this can be improved for a 3D model as well to improve the accuracy. And then either way, even if it is not a 3D case, we can generate a lot of simulations under this and calculate values to do further data analysis. And so that brings me to the end of my presentation. And before moving on to the Q&A session, I want to thank a very special set of people in my life. First of all, Dr. Ben, thank you so much for all the help you have given me. You have been a great mentor and excellent teacher for me. Honestly, part of me didn't want to finish this PhD project because I didn't want to stop working with you. So, yeah, and also to my committee members, thank you so much for allocating time for my work. I really appreciate that. And also to all the faculty members here in our department, I have learned a lot from you guys. Thank you so much for that. And also my parents and my sister for helping me to be the person who I am today. And my wife's family for accepting me as their own. And also to all my amazing friends out there, you have been great and you have been helping to make the ride more enjoyable. And finally, my wonderful wife, Kasunpa. Well, I will need another 45-minute presentation to tell how much I love you, so I'm not going to do that here. Thank you so much for giving me the opportunity to become your husband. So thank you so much, guys, and I'm happy to answer any of the questions you might have.
Any questions?
Yeah. First off, great presentation.
Thank you.
I noticed that the specifics of the aneurysms were in the cerebral aneurysms. Is there anything that prevents this model from being used for aneurysms in other places in the body?
The thing is, Brian, although the main reason why I said cerebral aneurysm is we ran some simulations. I didn't show that in my presentation. For those simulations, we only had the data for the cerebral aneurysms and on that top part. But still, this model should work anywhere, but it should have a bifurcation in it. But if it doesn't have bifurcation, maybe we can like change this a little bit, and we can even utilize it for a sidewall aneurysm too. Yeah. Please.
I congratulate you. This is very exciting stuff. I'm Charlie Prestigiacomo. I'm one of the neurosurgeons over at the main campus. One of the things that I find very exciting about this is the ability to take idealized resolutions of mathematical equations for aneurysm rupture status or aneurysm rupture risk, identify what the ideal quote-unquote aneurysm might look like when it ruptures, or the ideal aneurysm that will never rupture, allow you or this model to create those idealized versions with minimal changes in any parameter, but more importantly, what I would love to see is what happens when you change just the one parameter. And I think that this is an incredible tool that would allow us to look exactly at what kind of effects changing the geometry of the neck of an aneurysm would have in the overall behavior of that aneurysm with respect to the classic things. The one thing that I think would be wonderful, and we did something similar to that in 2009, taking an in vitro model of another investigator and created an in silico model. One of the things that I think would be great to do is to apply pulsatile flow to this, number one, and then number two, instead of a rigid boundary condition, apply an elastic boundary condition that would also have to be slightly variable in the aneurysm as opposed to the walls. Because one of the biggest criticisms that clinicians will have, and Ben and I have talked about, Dr. Vaughn and I have talked about this many, many times over the years. One of the biggest criticisms that I have to fight with my partners who don't do this or understand this is that this is too idealized to be applicable in the real world. And I always push back and I always fight back. And I say, no, not quite. At the very least, it puts you in the right ballpark. I think that if we can get closer with some of the inputs, there'd be less opportunity for some of the other individuals that may not understand all the nuances to be able to argue against the validity of this information and these models. Again, congratulations. I think there are plenty of questions that I would love to ask about how you can modify the angles based on Murray's law and conservation of energy to prove that indeed that's what happens and that there might be aneurysm formation when Murray's law isn't conserved. But I guess that's for another time.
Thank you so much. Okay.
Let's thank the chair again. And then, so at this point, it's the committee needs the chair, so if you don't mind, I'll stepping out.